Thank you. So I think we can get started. So thank you everyone for coming to this session. So this session is a workshop about deep learning. And we have two speakers from Esri, David and Katharina. They will give us a workshop regarding deep learning, and also follow that. We will have a Q&A sessions, and then we will have a demo, a live demo, like how to use these tools in, I believe it's Arcgis Pro, right? So so this is about this session. And before we get started, and I want to go through some logistic things, like you see from the slides. Then we do have a website, and you can visit our website. So it's not only a website for UC Jazz Week, but also it is a website for all the resources, especially jazz resources across UC campuses. And if you want to check out resources, you can visit our website. And also we do have a Slack channel, and it's also listed here. Let me put a message to chat. So it includes all this information, and join us on Slack and join us on these different channels, and keep update to all these informations from our UC Jazz Week. And we do have a code of conduct to comply with. And it's also in this chat. The link is in the chat, and check it out. And we have an event survey. So we appreciate it if you can give us some feedback for the event, and it's going to help us to organize this event in the future. So without further ado, I'm going to hand it over to Katharina, and let's get started. Thank you.
Thank you, Jiwan. Let me quickly share my screen here. I will not take too long. Let's see, like screen on here. Okay. So what we're gonna talk today is actually using deep learning in ArcGIS, and I just want to say that the one that we're gonna use in this workshop is ArcGIS Pro. So some of you probably familiar already with ArcGIS Pro, but the same things we also can do it in the notebook. So we have ArcGIS notebooks that can do the deep learning as well. And David Yu is our data scientist at Esri, and then you're gonna hear as well in the video that he's gonna introduce himself. So the design of this workshop is actually a recorded workshop first, about 26 minutes. Then after that, there is a live QA by David. Okay. And because we still have time until 1 hour, David also gonna bring live demo, and he gonna bring the latest example, which is the deep learning for vegetation encroachment. So it's very exciting session in here. With that, I'm gonna stop share and hand it over to David.
Awesome. Thank you, Katharina. Let me share my screen here. So as Rena mentioned, that the first thing that I'm going to play is around 25 minutes of video. So I will ask everybody to reserve their questions for the Q&A session. And for the demo session, feel free to ask as many questions as you would like. So without further ado, let me start the video. Hello, everyone. Thank you for attending this session. Sorry, let me make sure that I can share the sound as well. Okay. Today we will be talking about see what others can't using deep learning in ArcGIS. First off, a little bit about myself. My name is David Yu. I'm a data scientist on the GeoAI team here at Esri. My background is in computer science, whereas Esri had traditionally been a GIS company. And what that means is I spend a lot of my time trying to bring the latest and greatest tools and technologies, processes, and practices from the world of machine learning to solve real-world GIS problems. And in particular, I work on things like object tracking and anomaly detection, pattern analysis, and more recently, generative networks. So we begin by reviewing the definition. You know, we've all heard about AI. It's really become this buzzword in recent years. But what do we mean by an AI-enabled imagery workflow? And how do we quantify the effect of its application? So technically speaking, AI is a paradigm of computing to get computers to perform tasks at the level of a human, if not better. Whereas machine learning, which is another term that we hear about a lot, is a specific implementation of AI that's all about learning from large quantities of data in order to derive rules and recognize patterns without being explicitly programmed to do so. Deep learning, on the other hand, is really what we're interested in today, and what I will be showing you in a little while. It's a machine learning technique that's been gaining a lot of traction these days, which leverages deep neural networks to analyze high-dimensional data like videos and images. At a higher level, all of these deep learning workflows within ArcGIS consists of the following steps. You start off with your training data. These are typically large volumes of imagery which can be efficiently managed by ArcGIS. Then ground truth labels can be created on top of your rasters, and these can come in many forms. They can be bounding boxes for object detection, semantic masks for semantic or instance segmentation, or class labels for pure classification. Data prep is another important step where we can leverage ArcPy or ArcGIS Pro in order to export imagery into various formats that a deep learning model can then consume. So these formats would be something like Kitty labels or Pascal VOC if you're interested in object detection, Mascar CNN masks, and so on. After this, the ArcGIS API for Python can then apply image augmentation to your data, either using intelligent defaults or transformations that you specify. Model training, which is an important step, can then be done within ArcGIS Pro or the Python API. And we also give you a lot of CAN models to choose from, but you also have the option to integrate your own models through a simple raster function. As for inferencing, it's often the performance bottleneck for a lot of our clients. So here we support inferencing at scale through image and raster analysis servers, and enables you to carry out advanced analytics on top of those deep learning results. So these are basically post-processing tools. And by the way, all of these tools are native to ArcGIS. And then finally, these results can then be used and visualized in a variety of end information products, such as dashboards, web apps, and field apps. So I talked about the Python API. We really recognize that in this day and age, Python has become the language of data science. So we put a lot of effort and time into making sure that all of our deep learning capabilities and tools and libraries are made available through a Python API module, which we call arcgis.learn. And what this Learn module does is it provides a streamlined experience to get your data science project off the ground. So for those of you who are data scientists, you probably recognize that getting a model to work from scratch requires a lot of boilerplate code. So you'd have to start off with, writing your own training and validation loops. You have to specify a loss function. You have to figure out what is the optimal learning rate to use. In that case, you'd probably use something like AutoML. You have to write your own optimizer. And if you use PyTorch, you'd also have to write your own dataset and data loaders, which is especially difficult to do if you're working with geospatial data. So this is the type of work that we're aiming to simplify with the ArcGIS API for Python. So now with the Python API, in order to get a model training off the ground, it's very simple. All you would have to do is use one single line of code to instantiate your model. And then to train the model, it's model.fit. And over here, you can see that we're also specifying what is the learning rate to use. So we have a handy tool called the learning rate finder that returns what is the optimal slice or region where to choose your learning rate from. And by the way, all of these deep learning functionalities and classes from the Python API are based off fast.ai, which, if you know PyTorch, is basically a PyTorch wrapper. And of course, you have the option to override or replace some of these functionalities with your own implementation. And we give you an easy way to integrate your own model as well by specifying a Esri model definition file and also an associated Python raster function. So I also want to stress that the features that are included in the Learn module are not limited to only the training part, but basically every single step of that end-to-end pipeline which we have just talked about is represented here in the ArcGIS API for Python. So everything from data prep to model management to the inferencing APIs and so on. So the first example I'd like to dive in straight away here is accidents prediction. And if you're familiar with machine learning, this is not an uncommon workflow. Basically, the central question that you're asking is, can we predict the risk of a car accident along roadways? And if you think about it, there's really tens of variables at play here. So first of all, there is temporal factors like what is the time of the day, what is the day of the week. and also weather patterns, things like if there's any kind of snow coverage on the road, as well as spatial factors. So things like if there's any curvature on the road, how far is the accident away from an intersection, and so on. So really there's tens of variables, and it's impossible for a human to be able to understand what is the precise combination of each one of these variables that may lead to a higher risk of an accident. So this is really where machine learning would be able to help by analyzing this high dimensional data. However, what people don't realize is just how much insight a GIS-centric approach brings to the table. So in order to motivate this, I have a link here to a story map on the impact of geographic considerations towards accidents risk. So when we consider a problem like this, let's first think about what factors definitely contribute to the likelihood of an accident. How about the number of cars on the road? Obviously, this type of data is going to be a little bit difficult for us to come by, especially if we're thinking about collecting highly granular data at regular intervals, perhaps in real time. However, for our purposes, it's going to be good enough for us to make use of something much simpler. Let's say a population density layer that's going to be a good enough proxy for us to understand the number of cars on the road at any given time. Something else that we might want to consider are the various physical attributes of a stretch of road. So let's say we have a road here that I can kind of pan around and play around with. And let's say we have a good understanding of some of the physical attributes like the number of lanes on that road, what is the surface type of that road, what is the speed limit that's been imposed on that road, and so on. So why is geographic context important in this situation? Well, let's say we have this road versus some other road that has the same physical attributes. So let's say for the second road, it has the same number of lanes, it has the same speed limit, it has the same surface type, and so on. Well, how can we differentiate the two? Well, we can do so by bringing in additional contextual information, let's say geographic context. And if we place this in geographic context, we can see immediately that the second road kind of hugs along a mountainside and has a steep drop off to one side and perhaps some obstruction on the other side that prevents the driver from looking across here. And this may raise the likelihood of an accident versus the first road, which lies in a flat plain with good visibility on both sides. And you can very clearly see that it's going to be pretty difficult for you to have an accident here. So this is why geographic context is important. So let me show you some of the model results that we have. So here is running a model within ArcGIS Pro, and specifically we're using the scikit-learn library, and we are using XGBoost to understand what is the level of risk on a per road segment basis. So you see all of these road segments are color coded, and they have been color coded according to the risk that's assigned it by the model. So green obviously represents low level of risk, whereas orange and red represents regions of high risk. And we can see these red dots here that correspond to locations where accidents actually happened. And we can see that they essentially just lie on road segments that the model has predicted high likelihood of an accident for. And coming back to the point of GIS, what ArcGIS allows you to do is to be able to perform this type of end-to-end analysis. So it's essentially a framework for you to perform data collection, measurement, visualization, analysis, planning, and finally turning that data into actionable insight. All of that is available within ArcGIS. And from a deep learning perspective, here are basically the 4 key imagery tasks that you can perform with deep learning in ArcGIS. So first of all, we have pixel classification, and in the world of machine learning, this is also known as semantic segmentation. This is basically the task of assigning unique values, class values on a per pixel basis. Then you have object detection, which is all about returning that minimal bounding box or minimal bounding polygon over objects of interest. Then you have instance segmentation. So those of you familiar with something like MASCAR CNN will recognize that that's an instance segmentation workflow. So this basically combines the best of both worlds between object detection and pixel classification. One of the shortcomings of pixel classification is if we look at the example over here, we see that some of those houses, even though that they've been, very successfully segmented out, they're kind of joined together. And the model has no way of knowing what are unique instances of a house. So that's where you want to be able to segment out also those unique instances, and that's where instance segmentation can help. And then finally, you have your sort of standard machine learning, 101 model that allows you to be able to perform image classification. Now, the second demo I want to talk about is AI for disaster response. This is a project that we started off back in 2018 in October, essentially in the wake of Hurricane Michael. So for those of you who know, Hurricane Michael is kind of the worst natural disaster that happened in recent memory. It's something that made landfall in Tyndall Air Force Base in Florida, and it caused immense amounts of damage. So it had a maximum sustained wind speed of about 155 miles an hour, which basically makes it a Category 4 storm, very, very close to Category 5, and it essentially nearly leveled the entire Air Force Base in a matter of minutes. So unfortunately, disasters like this are becoming very, very common nowadays, and coordinating a response is becoming challenging in a number of different ways. Usually following a disaster like this, either a hurricane, earthquake, or flooding, certain agencies will go out and fly aircraft in order to capture a bunch of imagery in the area to be determined, in order to determine the level of damage. But all of that imagery needs to be processed somehow. And the way that this is usually done is that analysts would essentially sit down and manually comb through these hundreds and thousands of images in order to circle out locations where, structures may be damaged or roads may be blocked or have debris on them. And unfortunately, this takes a lot of time as well as effort in a situation where you don't have all the time in the world. So this is where we see an opportunity for parts of this workflow to be automated by AI. So our workflow is broken down into 4 pieces. First, we want to understand which structures are damaged. We want to know where people may be trapped and may need rescue. And we also want to understand if there's any spatial patterns, such as any clustering behavior for this type of building damage. And if there's any kind of hotspot, then we can isolate it and really prioritize rescue in those locations. So we first trained 2 AI models, one model in order to identify building footprints in an area of analysis, and the second model we ran on top of the output of the first model in order to classify them as either damaged or undamaged. And to show you what that labeling workflow looks like, this is it. Essentially, this is a web app that we've created. We understand that labeling is a very time-consuming task, and it's definitely not something that a single person wants to do. So that's why we created this web app for all of us in the office to be able to collaborate. We can have multiple people work on this at the same time. And we see that there's an underlying built-in footprint layer already, and in order to label it, it's very simple. We can just click on it and select from a drop-down menu whether or not it's damaged or undamaged. Of course, if we don't have access to an underlying building footprint layer, we can also just draw bounding boxes as well through this web app. So the second model that we've built is for detecting damaged roads. It's not enough for us to know which buildings are damaged. We also want to know what is the best way in order to route first responders to regions where people may need help. And that's where the second model comes in, because we want to know if there's any debris on the road, if roads have cracked, or if roads are completely washed away, and so on. So again, we are training an AI model in order to detect road debris. And this AI model trains very similarly to the previous models for building footprint detection and for damage detection, except in this case, we're detecting road debris. And again, this is a case where high quality, high volume training data would be needed. And again, we've built out a web app that does just this. So we can see that you can click on a segmented road and you can kind of assign it what is the level of damage and so on. So all of the training is done completely within the Arcgis platform, and this is the type of output that you can get. So now we see that the model is predicting that these regions have blocked roads or damaged roads. We can kind of switch back and forth in between them in order for you to see that, yes, these are indeed locations where, either trees have fallen down or if there's any kind of random debris on the road. And then the next piece is what I've talked about, and that is optimal routing. So we want to understand not only the location of damaged structures, not only which roads are passable, which ones are impassable, but we also want to automatically and intelligently route first responders from, let's say, their forward operating base to locations where people may need help. And in this case, we are using the ArcGIS Network Analyst extension in order to perform the routing task. So in this case, we've assigned a forward operating base to a local fire station here. And you see over here, these are the damaged structures. So, these red buildings, these red boxes represent damaged buildings. And by running all of this through Network Analyst, it's going to return the optimal route for us to, route these first responders to those locations. And then the last piece of this equation is getting this information into the hands of the people who are going to use it. So we utilized two things. First, we utilized ArcGIS Workforce, which is a mobile solution from ArcGIS. We also are utilizing the ArcGIS Operations Dashboard, which is essentially an end information product that allows us to be able to visualize some of this data. So first of all, the ArcGIS dashboard. In this case, we've created something like a situational awareness dashboard that allows us to be able to see what is the level of damage for buildings and roads. And we also can, see a breakdown of what is the level of damage in this area of analysis, right? So for the current extent on the screen, we can see that, what is the severity of the building damage, what is the rough cost that's been incurred by the storm on this area. So the average damage per building, as well as, what is the number of damaged roads and what is the number of damaged buildings. And the other part is an internal dashboard that's kind of exposed to analysts. So now someone at HQ who's, let's say, monitoring this response will be able to keep up with live progress updates from all of the first responders from out in the field. And we can kind of see, the same information, but we also have access to information like what is the location of all of those operators out in the field, what is their current task, and what is their level of completion of the current task. Let's say, if they're rescuing somebody. And then finally, just to conclude on some very cool visuals, following this successful project, we also collaborated with Microsoft and brought this workflow into Azure Stack Edge, which is basically their edge device. And this piece was actually presented at the Microsoft Ignite conference in 2019, where we showcased the same damaged outputs, but now in a 3D scene, which I think also attests to the versatility of the ArcGIS platform. And here's kind of that final 3D scene output. So with that, I'd like to dive really quickly into a demo here that showcases some of those end-to-end components that we have just talked about, specifically those end-to-end components that exist within ArcGIS Pro. So you can do the same workflows within ArcGIS API for Python as well. So the problem that we're interested in solving is we want to be able to classify clutter classes. Essentially, these types of zoning information. So we want to understand what part of the image constitutes high-risers, what part constitutes commercial urban versus commercial suburban versus residential versus public. And by public, I kind of mean, parks or public facilities. So of course, with any deep learning workflow, the first step that you have to do is create some training samples. So I already have an imagery layer that's brought in here. So this is basically a NAPE image that I've been able to obtain from the Living Atlas. And I've then proceeded to clip it out according to this boundary here. So this is our area of interest. And this image is basically 1 meter ground resolution imagery. In order to create those training labels, it's very simple. All you would have to do is highlight your imagery layer. And then inside the imagery tab, we have a button called classification tools. And within here, you can specify that you want to use the label objects for deep learning tool. And this is basically what shows up after you click that tool. And to draw some training labels, let me first click them on. So these are some pre-drawn training labels, but in order to draw more, all you would have to do is select from one of these tools. My personal favorite is the freehand tool. You can basically click that and start drawing away. And as you can see, these are color-coded according to their classes. The next step after this is export training data for deep learning. So it's very important to do that pre-processing step because obviously a machine learning model by itself is not going to be able to take in just this giant raster. You would have to somehow tile it out into smaller rasters and also tile out the corresponding labels as well. So in this case, it's a geoprocessing tool. You can specify what is that tile size. you can also specify the most important thing, which is what is the metadata format that you want to choose. So in this case, you can see that I've selected label tiles because I'm interested in a object classification workflow. Whereas if I were interested in, let's say, object detection, i.e. coming up with bounding boxes, I probably would choose something like kitty labels or Pascal VLC. Whereas if I'm interested in semantic segmentation, then I would choose classify tiles or RCNN masks for instance segmentation. And then I can click run on this tool, and what comes up in the output is basically a couple of directories. So we first have a directory containing all of these images that have been shipped out. And then we have a directory containing all of the labels that correspond to those images. And of course, some other metadata formats here. The next step after that is training the model. And of course, you can do this either within Pro or within the Python API. So I'm going to show the Pro step for now. It's again a geoprocessing tool. It's very simple. It's called Train Deep Learning Tool. And all you would have to do is specify your training data. So in this case, you would basically have to drag in this folder that was just created from that previous step. And the tool is kind of intelligent enough to figure out that, hey, because the metadata that you have selected for the previous step was essentially for object classification, I'm only going to give you models that pertain to object classification. Whereas, let's say you chose Pascal VLC as a metadata format for the previous step, then the model type is going to give you a bunch of CAN models for Pascal VLC formats. So something like SSD or faster RCNN and so on. And of course, you can choose some other advanced parameters as well. So in this case, you can specify what is the depth of that backbone model. And that really depends on what is the complexity of the problem space that you're dealing with. In this case, ResNet 34 would suffice. So I can then run this model here. And this model actually took less than 1 hour to train. So let me show you some of those inference results. But first, in order to perform inference, it's again another geoprocessing tool. And in this case, it's called classify objects using deep learning. We actually have two more tools that deal with object detection and also semantic segmentation. In this case, it's just classify objects using deep learning. You would have to pass in the input raster and click run. And in the output, this is what that looks like. So let me turn off the actual training labels here for you to get a better look. And we can zoom into some interesting areas here. So for instance, we can zoom into this location where we can see that in the background, these are basically just parks, right, or public facilities. And as you can see from the symbology information here, that these have indeed been classified as public. And some of these other areas that have a lot of concrete or basically large structures, these have been classified as either suburban or urban commercial zones. And one interesting thing that you see as you start moving closer to the city center is that you see that there's definitely a lot more commercial buildings as opposed to residential buildings, which are these gray buildings, gray tiles over here. So that was just a very quick demo on how you can employ a end-to-end deep learning workflow completely within Arcgis Pro. And I want to quickly switch gears and also talk about some of our machine learning and 3D capabilities as they pertain to point cloud data. So within ArcGIS, we're not only able to host, manage, and analyze LiDAR point cloud data natively, but we're also able to introduce machine learning into the mix and come up with a bunch of useful workflows, such as the one that you see here, which is 3D building reconstruction with correct roof form prediction. So this was achieved through a combination of machine learning approach to predict 7 different types of roof forms by analyzing rasterized point cloud data, as well as extrusion through our 3D local government solution. And we're able to show the finalized product through a web scene, which is what we right. So here are some additional resources to learn more if you're interested. And thank you for listening to my presentation today. Okay, so that was the video demo. Are there any questions from the audience at this point?
And thank you for the presentation. And personally, I'm interested in the geospatial one, the network analysis. This looks like the deep learning is not a module. So it's like they say embedded into multiple functions, like you just showed, like it is in classification, it is in network analysis, and it is in other things. So it's not specifically module, but it is like applied to different functions that in Arcgis Pro.
Right, exactly. So we don't necessarily have a single product for deep learning. It's really embedded in most of our offerings, right? So I would say the easiest entry point would be through ArcGIS Pro, because that's where you can conduct a lot of deep learning imagery workflows and all of the vector machine learning imagery workflows as well. But another good entry point is, if you're familiar with Python, then the ArcGIS API for Python, because there's an entire module within the Python API called the Learn module, where we have all of the models that are stored there. So things like single shot detector, Mascar CNN, all of those models are available there. And we can also leverage the pre-trained models within the Living Atlas. So that's a publicly available website that you can download models from. So we have pre-trained models for things like detecting building footprints, detecting land cover classifications, and so on. But also deep learning capabilities are embedded across other applications, such as our field apps. So for instance, one of those apps is Survey 123. The idea is, if you want to go outside and take a picture of, let's say, a tree, and have the model detect in real time what type of tree that is using just your mobile phone, that's also something that we have as well. So it's really, yeah, it's everywhere, and we're continuing to update some of these capabilities across our entire stack.
Okay, so I just noticed there are questions from the chat. So what are where are the links to the resources you just showed in the video? Would you mind posting?
Yes, actually, Rena, would we be able to share the slide deck with the attendees after this session?
Sure.
Yeah, okay, we can do that.
And also there's another question. So is the video available for us to watch again? And because part of it came in a bit blurry on my side.
Yeah, I do apologize for the blurriness of the video. It is available on YouTube. I will post a link in the chat momentarily. But that's kind of why I also wanted to do the second demo, just to walk you through some of the more like the exercises in Pro, because yeah, the video is a little bit blurry. Apologize for that.
Sure. Yeah, I think we can go to the demo part, and probably you can share with us all these links at the end of this workshop.
Sounds good.
Thank you.
Okay, give me 1 second here. Okay, yeah, so I will post the YouTube link and also the associated resources link after, well, at the end of the workshop. So let me share my screen again. Okay, can you see my screen?
Yes.
Perfect. Okay, so this is a really interesting scenario. This is for vegetation encroachment, and it's intended for people who are, let's say, utility providers. But I think what's really neat about this particular demo is that it involves basically every single component in the end-to-end deep learning pipeline from ArcGIS. And for those of you who do not know, vegetation encroachment is the #1 cause of outages in electric power systems in the US. And it can also lead to wildfires, which is very bad, which is not only an issue here in the US, but also in places like Australia as well. And usually a lot of the utility providers, what they would do is to actually have inspectors drive hundreds of miles of streets in order to visually inspect every single tree for possible signs of encroachment. And by encroachment, I mean things like what you see here, where the tree is overlapping an existing power line. So utility providers would have access to all of the underlying power lines just as a feature layer. But the idea here is, well, can we use some kind of automation to understand if there are signs of encroachment without having a person to actually drive hundreds of miles of streets? And This is exactly what we can do using deep learning, using the same workflows that I've shown earlier in the videos. So the first thing that we can do is run a model in order to detect all of these trees here. And as you can see, we've extracted all of these tree points within 40 meters of a power line. And so that's why you don't see some of these trees in the middle being detected here. So that's the first step. And then the second step is understanding levels of encroachment. So we want to know if there are certain trees that are farther away versus trees that are closer, because the ones that are closer should definitely be prioritized, which is what we see in the second feature layer. These are being color coded according to their distances to these power lines, red being urgent, yellow and orange being not so urgent. And what's also really good about this particular workflow is that we can use the same process to not only detect trees, but also other interesting features as well. So things like building footprints, things like roads, and even assets like utility poles. Because a lot of the utility providers, they don't actually have access to the precise locations, latitude and longitude of their utility poles. Sometimes when these poles are first constructed, it was just pen on paper, and the actual latitude and longitude pair is not really precise in their database. So this is just another way for them to verify whether or not these are correct in their asset database. So I think you can imagine how easy this would be just to do this manually, right? By sitting down and manually digitizing some of these features. But if you really want to run this at a citywide or even statewide or nationwide scale, then it's imperative that we use machine learning techniques to try to automate this process. Another really interesting thing that we can do is we can actually throw everything onto an operations dashboard in order to understand for every single area that I'm looking at, how many miles of power lines are in need of treatment, and of those power lines that are in need of treatment, how many locations is there for urgent risk, how many locations are there for high risk or moderate risk of encroachment. And as I kind of pan out here, you can see that the dashboard will get automatically updated according to the extent that I'm looking at. And for this particular demo, we've actually run this analysis over the entire city of Manchester in Connecticut, which is about 500 miles of power lines. This is definitely a lot of data, but using machine learning, we can really do this in a matter of hours or minutes instead of days or weeks. And one other thing that I just want to show is that we can leverage all of the pre-trained models that we have available on the Living Atlas to do this type of work. So this is kind of what I alluded to earlier, where if you just go to livingatlas.rgs.com and search for deep learning, these are all of the models that we currently have, but they're being updated all the time. So we're continuously injecting new models into this particular page. Some of these you see are relevant for this particular example, such as tree point classification or building footprint extraction and so on. But then we also have a lot of data, a lot of models that pertain to 3D data as well. So if you have access to LiDAR data, then we can also use like power line classification models here, or we can use other kinds of LiDAR models as well. And there's also models for extracting roads. So pretty cool stuff. This basically prevents you from having to train your own models from scratch. You can basically download these models, see if they work. If they don't work, feel free to bring in your own data set and then just do model fine tuning. So you don't have to spend like hundreds of hours to train a model. So how do we actually do the end-to-end detection part of picking up some of these trees? And that's where I want to bring in ArcGIS Pro. So I showed this a little bit earlier in that video, but unfortunately that was a little bit blurry. So I just want to show this again. First thing is we do provide data labeling tools inside ArcGIS Pro. So if you remember the end-to-end workflow, this data labeling is really the first step, right? You need to be able to have some kind of labels for your model to learn against. And for trees, we offer the ability to just draw bounding boxes over some of these trees. And I can call this a tree class, give it a default value of 1, and just click OK. So that's automatically going to create a new schema for me. And I can just keep on labeling some of these trees. Now, generally, depends on where you're trying to run inference or training. There can be a lot of different types of trees, right? So for instance, over here in Connecticut, we see that sometimes in the winter, a lot of these trees lose their leaves. So it is important that whenever you create these kinds of training labels, you try to capture as diverse a training set as possible. That generally will give you a more accurate model in the end. So this can take a while, which is why in that previous video, I also showed you can do this using a web app as well, just to enlist help from coworkers or colleagues and so on. So everybody can get a go at labeling. But once these labels are created, the next step is to be able to export that into a format that a machine learning model can then understand. So as we can see, this is quite a large raster, right? This is a very big satellite image. So we obviously just can't feed that directly into a deep learning model. We'd have to somehow be able to chunk it up into smaller tiles and also export some of these bounding boxes into the appropriate metadata format. So this is where the tool export training data for deep learning comes in. This tool is also available within ArcPy if you want to do this in a more programmatic fashion. But the idea is that you simply provide the input raster that you want to tile up, and then you can specify whether or not I want the image to be in JPEG or TIFF format. And the important part here is the metadata format. So for those of you who've tried your hand at deep learning workflows before, you'll probably know that even for bounding boxes, there's a lot of metadata formats that you can choose from. Pascal VOC is one of them, but there's also things like kitty labels. And let me click this drop down, which, there we go. There's also things like kitty labels and well, a bunch of other things like RCNN masks, label tiles, and so on. So this is where you can specify that metadata format. And then all you would have to do is click run. So let me show you the output of running that particular tool. What that tool is going to provide is essentially just a folder containing both your imagery and also your labels. So if I click open imagery here, you see that these have been tiled up into essentially 256 by 256 sized tiles, and you can group them into a batch and feed it into a model. But also the labels, these are the Pascal VOC labels that are stored in an XML format. So now you have all of your data exported. The next step is to actually start training a model. How we would train that model is again by using a tool, a geoprocessing tool within ArcGIS Pro, and it's called Train Deep Learning Model. So over here, we can actually provide that training data, which is that just that exported folder that we've created before. We can literally just drag and drop that into this tool here. And the tool is sort of intelligent enough to understand that, hey, by looking at some of these exported images, we see that the labels are in Pascal VOC format, which means that you probably want to do object detection as opposed to semantic segmentation. So in the dropdown for the model type, it'll restrict you to the sort of object detection models that we have available. So some examples of those are single shot detector, RedNetNet, YOLO v3, faster RCNN, and so on. But if you just try to pass in some other input folder for, let's say, semantic segmentation, then the model type is going to reflect that. It'll only provide you the available semantic segmentation models. And it's important, obviously, whenever we try to train a model to utilize the GPU, which is why in the environments tab here, we want to make sure that the processor type is set to GPU instead of CPU. So once this is set, all we would have to do is click run. But before I click run, I just also want to show you that it is possible to change the backbone as well. So if you're familiar with kind of creating your own models, you're probably familiar with swapping out different types of backbones depending on the complexity of the problem. So if you have a very complex problem, you might want to use a very deep backbone, right? Like ResNet 101, for example. So you have the option here as well. So once the model is trained, the next step is to try to go to a new area where the model has not been trained against. So I'm going to go to this particular bookmark, and it's time to run inference for that model. So it's again a geoprocessing tool that we can run called detect objects using deep learning. And all we would have to do is provide the input raster and provide the trained model. So just to give you an example, what that trained model looks like, it's just a zip file. Let's see here. So here it is. It's a DLPK format, which stands for deep learning package. But what this really is just a zip file, and containing within that zip file is a file that's a metadata file and also the model weights, right? So because this is running PyTorch under the hood, we have a PTH file for the weights. So we just have to drag this in and then specify some hyperparameters, such as what is the threshold, confidence threshold, what is the batch size that you want to use depending on the size of your GPU and so on. And then we can click run. I'm not going to run this here because it will take a little bit of time, but the idea is you can train a model to detect trees, but also other features such as buildings, roads, and also utility poles as well. So all of this can be done very easily end-to-end using ArcGIS Pro. And again, as I mentioned earlier, if you want to run this within the Python API, there's a lot of great documentation that I'll be able to share with you at the end of this demo as well. So all of that is really easily done. And one more thing is, for the case of vegetation encroachment, sometimes it's not enough just to understand where the encroachment is. Sometimes you want to go one level deeper and ask, what type of encroachment is it? Because depending on whether or not the encroachment is above or underneath the power line, it represents different levels of risk. So this is where additional data inputs like LiDAR comes in very handy. And what I have here is a web scene that we've collected. So these are all data that we've collected over a city in Australia. And as you can see here, these are just unclassified points, right? Right now, the color simply represents the elevation. But again, using some of the pre-trained models that we have in the Living Atlas, we can immediately run deep learning classification over these and understand which points is part of a tree, which points represents a power line, and which points represents ground points or buildings. We can also do some really cool visuals like extracting out the 3D building shells automatically, and all of this is being done within ArcGIS Pro. But immediately we can have access to the next level of detail, which we didn't have before, just looking at the 2D case, because we can see immediately the exact locations where intersections happen between these utility lines and the vegetation. And what's really cool is now we can sort of analyze the spatial patterns of encroachment and try to distinguish between encroachment from underneath, right, which is what you see here highlighted by the yellow points, which is not necessarily dangerous because, well, the branches are kind of underneath the power lines, versus something a little bit more dangerous, which is encroachment from above. So this is particularly dangerous because there's always the risk that some of these branches may fall and make contact, causing an outage or wildfire. And then the most dangerous category we have is intertwined. So this is where vegetation is already intertwined with the power lines. So these are the parts of the branches that need to be immediately trimmed. So this gives us access to that next level of analysis, which is missing, again, from that 2D case. And as with the 2D case, you can probably see how this type of work can be done manually and is in fact traditionally done manually. But if you want to run this type of inference at a, let's say, citywide or even nationwide scale, like we have here, really you need to bring in some of these deep learning capabilities. So yeah, I think this just attests to the power of deep learning, because we can basically run this operation in a matter of minutes and hours instead of days and weeks. So that's my final demo. And with that, I'd like to thank you very much for attending the session. And let's see if we have any interesting questions.
Okay, thank you. And we have a question from the chat. How many building footprints do I need to create a model for building instruction so that it would perform well?
Yep, that's a very good question. And I think it really depends on where you're trying to run building footprint extraction. So in that Living Atlas page that I showed earlier, we have a model that performs very well over the entire USA. We also have another model that's trained over different geographical regions. So we have a model that's trained over Africa. But let's say if you want to perform inference over South America, then you'd have to do some kind of model fine tuning. So one thing that you can do is download the Building Footprint USA pre-trained model and then provide, I would say, up to thousands of examples of building footprints for your model to be perfect. Again, that's just a ballpark figure. It's really difficult to say exactly how many examples they would have to provide. Generally, we would recommend try to provide, like a couple of thousand examples, train the model, see how it performs. And if it is underperforming in certain areas because there's different types of buildings that are maybe not represented in the original training set, then try to collect data over that new area where that model hasn't been trained against. So it's definitely more of an iterative process as opposed to saying, hey, let's just bring in 10,000 examples and after that the model will be perfect. So there is a little bit of experimentation involved.
Thank you. And also, this is for the training data, but I think the Arcgis Pro can also do the training without, not the training, do some analysis without the training model. Like you put in the word imagery data and want to identify the different trees. But is there a way to identify the trees without putting the training model? So for example, I don't want to select the trees by myself. Can the deep learning function do that?
Yes. So, well, not necessarily deep learning, because for deep learning models, you would still have to train a model unless it's using some of the pre-trained models that we have on the Living Atlas, right? If you want to, let's say, have an easy way to select certain trees, there are a lot of imagery tools that we have available that allow you to do that. So,
like the roads, like the lakes, etc. They are quite common, right? I mean, you don't need to put in some training data to identify them.
Right. I mean, so let's see here. So as an example, we have the classification tool that allows you to perform things like segmentation. So if we select segmentation, think about it as very similar to the magic wand tool that you have in Photoshop, right? The idea here is we're now using not necessarily deep learning, but imagery-based techniques or computer vision-based techniques in order to distinguish between a field here versus the forest area that we have here. So these are the kinds of tools that you can use to help create training labels for your subsequent deep learning model. That's one thing. Another thing is it really depends on the complexity of your problem. If you're just trying to do land cover classification, let's assume that this is a lake, right? Then it's very easy to just use a classification wizard to create a, let's say, random forest or a support vector machine model, which will train just using like 3 or 4 examples, and it'll give you really decent results after like 10 minutes of training. So just to quickly show you, let's select supervised training methods, and we want to do pixel-based classification. Is it asking me to do more things? Okay, I guess the tool has changed over time. Let me just walk you through the workflow then. So the idea here is, let's assume that this is a water body. Then we can just use the freehand tool, right, to draw some training labels over that water body. And that's data that we have that we can use to train something like a support vector machine in the classification wizard. And there's a lot of resources that you can find online for this, but the idea here is that you would only spend 10 minutes training a model, a very simple model, as opposed to like, an hour training a deep learning model.
Yep. Okay, thank you. And also, I saw you showed us the vegetation encroachments in 3D view, and so could you show us how can we use that function from the Arcgis for this layout? We saw the product, the final product that you want to show us. So what is the function we can use from this layout?
Yeah, sure. Unfortunately, I don't have that particular pro project ready, but I can talk about it. So the idea is that everything that you see in the end-to-end 2D workflow is really replicated for the 3D as well. So you have the same process of exporting your training data. So the first thing is performing labeling. Now, if you actually have a last point cloud in here, which I don't have, there is going to be an additional tab called classification that you can click, and this will allow you to draw 3D bounding boxes or like 3D spheres. Basically, these are labeling tools that allow you to color some of those point clouds. And once you have all of those point clouds colored, that's your training data. And then you can directly feed that to a point CNN model that we have. And that's something that I can also provide some resources for. But we also have some sample notebooks. Let me quickly find an example. Give me 1 second here.
Sure.
Okay, so if you just search for point CNN in ArcGIS Pro or in ArcGIS in Google, there's actually a lot of examples that we've shown, and there's documentation involved in how to use some of these point CNN models. So it is possible to do this within ArcGIS Pro. It's, however, recommended for more for these kinds of 3D workflows to do this directly within the Python API, simply because you have more flexibility. But to do this in Pro, you would simply use some of the available geoprocessing tools like prepare point cloud training data. So this is the 3D version of export training data for deep learning. And then you have classified point cloud, the 3D version of some of the classified pixel tools that we have in 2D and so on.
But the training data we put into the training model is going to be points instead of lines or polygons.
Correct. So for LiDAR data, the model that we have is point CNN, which natively ingests 3D points. But you can also, if you have, let's say, like a 3D mesh, for instance, there's also ways to just sample points from a 3D mesh for you to use a point CNN model. But currently, point CNN model is the only 3D sort of deep learning model that we have.
Okay, I see. So this captures the height or the elevation of the point data you put into it, and then, for example, I have the points for trees, and I have a points for the electric lines, the power lines. So how do they distinguish between these two?
Right. So it's not only capturing the XYZ locations, but also, let's say, the number of returns, the intensity of some of those points, the associated RGB if you have access to those. So let's see here. One other example that I can show is this Medium article for classifying these power lines. And so yeah, we're using, in this case, XYZ plus intensity. Not necessarily using RGB in this case, but if you have colored points, that can also be ingested. But that's basically all the information that you would need to train a point CNN model. Because the model takes into account context, so it's going to look at these kind of like really large 3D voxels of the area, it will be able to distinguish between a power line and, let's say, a tree, right? And all of it is just dependent on how much training data that you provide. So if you have a lot of training data, even if some of the things that you want to detect are quite sparse, like the power lines here, the model generally still performs quite well.
Okay, I see. Yeah. So last question. So I want to know, are these tools available for, like, for example, a standard Arcgis Pro? Because I'm from UCLA, and we have the license for Arcgis Pro provided to our campus, to our community. So is this too the 3D cloud, point clouds, too accessible to people if we have a standard license for Arcgis Pro?
I guess that's more of a question for Rena. I know that for the 3D stuff, we need the 3D analyst extension. And for some of the 2D deep learning tools, we need the image analyst extension for ArcGIS Pro. But I don't know if Rena has any additional input for that.
Okay. Nice. Because personally I use the Arcgis Pro often. So I didn't see these functions, so I was wondering if I missed something, or
yeah, it could be a licensing issue. So image analyst and 3D analyst, I think, are the two fundamental licenses that you would need.
Okay, yeah, I just saw a Carlos put a message to chat, and oh, okay, and I included production licenses. Okay, thank you, Carlos.
Perfect. And by the way, I think someone in the past asked, is there a link to the video? So it's on YouTube right now, so I am pasting that link here. So yeah, so that's just a link to the video. One other thing that I'd like to provide a link for is our Medium article, sort of Medium blog page. So this is where we have a lot of in-depth technical blogs for all of well, for some of the examples that you've seen in the past. I think these are quite cool because they tell you exactly what steps are taken in order to arrive at some of these interesting results. For instance, the disaster response workflow that I showed is also available as a Medium blog post. So let me also just put that in the chat here. Just feel free to take a look if you're interested.
And also, I think there's another question asked for the link to the Medium article.
Ah, yeah, well, that's right here. That's just the link I provided.
Okay, awesome.
It's available here. Yeah.
Awesome. So thank you so much for sharing with us all these advanced tools. And I think it's very useful for both researchers and all the people who are interested in them. And also, as you mentioned, helps the decision and make actions. And it's very smart and also useful too. So thank you so much. And also thank you for everyone attending this workshop. And this is the end of the workshop. And I hope you have a great rest of the day. Thank you. Goodbye, everyone.
Bye, everyone.